So we've been covering analysis of fluid systems using the concepts of linear momentum. Linear momentum is not conserved. It can be increased or decreased by what? Imbalance of forces. So we start with the general Reynolds transport theorem. Then we take into account the linear momentum, and this is what can increase or decrease the linear momentum. Often, the amount of linear momentum in the control system, steady state, it doesn't change. That term is zero. But over the control surface, you have linear momentum flowing with the mass in and out. Often, we just talk about some particular ports of entry and ports of exit. So we talk about inlet at this zone, and we talk about the mass flow rate coming in, carrying its average velocity, and the mass flow rate out with its average velocity. So that surface integral often is treated as a summation. What is this beta? It's the linear momentum correction factor, often zero, not zero, often it's 1, close to 1. Again, this is that transient term. What about the sum of the forces here? Remember that it's a combination of point loads. It's also influenced by pressures. Force per unit area. And let's see, if you have a force at a point, force per unit area, what's the next one? Force per unit volume, which would be a body. And the big body force would be gravity. So when you see these forces here, think of, do I have any point loads? Do I have any pressures or forces per unit area? And then do I have any body forces, especially gravity, force per unit volume? And taking those into account. Well, this is all nice, but we have to solve problems. I intended to solve this last time. Did I solve it or not? I don't think so. Okay, let's solve it. We have a horizontal 40 millimeter diameter pipe. So here's the pipe diameter is given to be 40 millimeter. And it has a volumetric flow rate. So Q is equal to 0.02 meters cubed per second of water. And it hits a 90-degree elbow. And then it's directed downward and diverts the water downward and discharges it into the air. The elbow is connected to the pipe by a flange, or it's mounted to the pipe. Determine 3 things. The force that the water exerts on the elbow. Then the force that the elbow exerts on the water, and the force that the pipe exerts on the elbow. So the order, let's get these clear. The force that the water exerts on the elbow. This one, the force that the elbow exerts on the water, and the force that the pipe exerts on the elbow. Would these in general be vectors? Yeah, vectors. And you can see that it probably has both an x component and a y component. So let's treat it as a vector. As vector entities, 2 of these will be the same. They'll be the same. One of them will be different because it'll be opposite of the other 2. So let's say you calculate one to be, 5I minus 3J in units of Newton because it's a force. The other one will be exactly the same, but one of the 3 will be the opposite of that. You see that? So what I'd like you to do is I'm going to pause. I'd like you to tell me which 2 are the same. Is it the force that the water exerts on the elbow, the force that the elbow exerts on the water, the force that the pipe exerts on the elbow? Which of those 2 are the same? Walk around. I'm going to walk around. I want to make sure everybody does it conceptually and write it down, okay? Well, I know that I can try and draw the control volume for the water. Wouldn't it look like that if I just focus on the water that's traveling through the elbow? And I know I have some inflow here and outflow there, but I'm going to have some net force that the walls of the elbow that are in contact with the water force, have an impact on the water. Do you see that? That's the first one. Not the first one, the second one. The force that the walls of the elbow have on the water. Of that, what, for part B, okay, can you tell me, would the force that the elbow exerts on that water, this is a control volume for the water, would it, in the X direction, would it want to go to the right or to the left? To the left. Okay, that's the correct answer. Why is that the correct answer in your own words? Because it has to completely stop the X direction. I like that answer. It's not the only answer. Another student could express it with their own words, but it's the same idea. It's the correct idea, right? What's happening in the X direction? The fluid's coming in, and it's having to be stopped. How are you going to stop it? Not by pulling it in the X, by pushing back. What about now in the Y? There's a net force that the walls of the elbow exert on the water. Is it going to be trying to up it, lift it up, or push it down? Push it down, the same thing. It comes in with nothing in the Y, but it goes out with a large down Y, velocity in the Y, hence there has to be a force to push it down. Now, if I had the weight of the water in here, then I got to say, well, is the weight of the water, blah, 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 and I got to worry about that a little bit because there's two things that help push it down then, the wall of the pipe, the weight of the water. So, but there's no weight of the water that I wanted to consider in this control volume. So that's the direction. So this is going to be the direction that the elbow exerts on the water. Okay. Now let's focus, this is harder to do, on only the walls of the, that's my bad rendition. There's only the walls of the elbow. Only the metal parts of the elbow. Does the water exert a force on the metal elbow? Yes. Would it be equal and opposite that the metal elbow exerted on the water? It would, wouldn't it? It's like, hold it, the water's pushing on the elbow's pushing back. So guess who would are equal and opposite? A and B are equal but opposite. True? So if I said that the force that the water exerts on the elbow is equal to negative the force that the elbow exerts on the water. Put a vector on that. Do you agree with that? Now with that, we know that A and B are not equal then. But which is C equal to? What is the force that the pipe exerts on the elbow? Is that equal to either A or B? That's the new question for you, okay? All right. If you think of, I'm going to just draw, I hate to do this, it's hard to do it, but isn't this my rendition of the free body diagram of the elbow? That's my poor rendition of the free body diagram of the elbow, right? Now tell me, what about the water? Does it push it to the right or pull it back to the left in the X direction? So the water has a net force in the positive X direction on the elbow. True? How about in the Y direction? What does the water do to the elbow? Push it up or pull it down? Doesn't that it? Is the elbow going to now start to accelerate because of this imbalance of force on the elbow? Or is the elbow going to be there stationary? What keeps the elbow stationary? The presence of the pipe. That is bolted or flanged or threaded, some connection to the pipe. So if I do a free body diagram only of the elbow, I would need to account for the force, not only that the water pushes on the elbow, but the pipe. The pipe. So to keep the elbow in equilibrium, is the pipe going to have to pull back or push forward? With confidence? With confidence. And what is the pipe going to have to do? Hold it down. It's going to have to hold it back and hold it down for equilibrium. So this, what I sketched in blue, isn't that the force that the pipe exerts on the elbow? These two right here are the force that the pipe exerts on the elbow. True? So which is true? C is equal to either B or A. Isn't it? A. Isn't it A? Now, I went through this slowly because it can be so tricky. But, you know, we can be asked a number of different questions. How do I solve for this? Please solve for that. Let's do this now. Let's focus on probably the first one I should have asked is B. What's the force that the elbow exerts on the water? So let's solve for that one first, okay? Force that the elbow exerts on the water. How am I going to solve for the force that the elbow exerts on the water? What's my strategy? We're going to do a linear momentum analysis on a clearly defined control volume. What is going to be my most logical, clearly defined control volume? The water. Focus on the water. Am I going to have any elbow solid steel parts in the control volume? Nope. Nope. See that? So we start with this one right here, which is only the water in the control volume. And we say, I know I have a net force from the walls of the elbow acting on it. And I'm going to, if I don't know the direction, I'll just assume it's in this direction and that direction. And then I'll work it out and I'll see, oh, it's negative or positive. Okay? But what do I have across this boundary? Inflow. What do I have across that boundary? Outflow. Do I have a pressure distribution across this boundary? Atmospheric pressure. So essentially we work in gauge because it drops out the atmosphere. But what about the pressure over here on the inlet? Okay, this is, let's call this one state 1 coming in and 2 going out. State 1 coming in and 2 going out. And I want you to say the pressure at 1 compared to the pressure at 2. Is it greater, equal, or less? And I want everyone to personally answer that question. And I'm going to walk around. And if it's different, how are you going to calculate it? Or if it's equal, how are you going to prove it? Now you got it. Somebody said, what about the difference in the water pressure if I go from the bottom of 1 to the top of 1? Isn't there a change in the water pressure because of gravity and hydrostatics? We're neglecting that. We're neglecting it. We're talking about the pressure over the surface 1 is 1 value, and the pressure over the surface 2 is 1 value. Okay? All right. And the consensus is that they're equal. Why are they equal?
They don't change speed.
They don't change speed and they don't change area. Yeah. And so who wrote Bernoulli's equation and went from 1 to 2? And didn't you deduce then, because the non-change in area, the density or the specific volume is the same, hence speed is the same. Neglect the effect of gravity, a little hydrostatic, forget it. Don't worry about the rho GZ. How many people were tripped up? They thought, oh, I got a higher elevation for one, just half the pipe diameter, hence it's less because of that. They didn't give you any information about it. Well, I know the diameter's there, but there's no weight of the water in there, and it's negligible. We're going to neglect it. Now, what would happen if this was an elbow that changed diameters? Do they even make it? Yeah, they do. It'll change diameter. Come in a 2-inch, it'll go out 1.5 inches, or come in 2 inch and go out inch. All right? You can buy them, but they're not as common. Then it would change, wouldn't it? Yeah, it would change. But here, constant area, hence the two pressures are the same. Now, do I have any point loads other than I'm going to do the resultant for the elbow on the water and put it as one force. I know that it's really the pressure, it's all along the surfaces of the wall of the pipe, but I'm going to replace that complicated force, distributed force system at the surface by one equivalent resultant force. So let's call this Fx and Fy. Can you tell, if you do then the linear momentum analysis, should we start with the most general equation? We have the sum of all forces equal to the time rate of change of that term 0. Then we're going to have the inflow, the beta, the linear momentum correction factor. What's the linear momentum correction factor for this problem? 1. And then we're going to have the mass flow rate, the V average, and that's on the inflow. I got to take a look here. Yeah, switched it around. Usually you write the outflow with the plus and then the minus with the inflow. But this will be the in and the in plus the beta m dot V average out. And those are vector quantities in the most general sense. Okay. So what are we going to put? We're going to have for the force, we're going to have the pressure 1 times the area 1. The average pressure at surface 1 times area 1. And isn't that all in the I? And nothing in the J at 1. What about the surface 2? Isn't that going to be plus P2A2 all in the J? So really that's all your forces. And then we're going to have mass flow rates the same. I'm neglecting the beta, called beta equal to 1. Beta equal to 1. And let's do the average. Let's do the out first because it's a plus. So what's the out? Isn't it a minus VJ? Isn't that the outflow? And then what about the inflow? I have to have a negative on the velocity in, but the velocity in, isn't that VI? I know that I'm doing a couple things here. I've got a negative on the velocity, average velocity in. The velocity in is all in the positive I direction. I'm going to pause. Does that look good?
Why did you put negative and positive Y?
The Y is downward directed on the outflow. Okay, so the velocity on the out, if I just focused on this one, is 0 in the I minus V in the J.
Oh, and it's negative inflow, which is, okay, I see.
And then I had a negative in front of the inflow. I just put the order, switched them. I don't know why I didn't follow the equation sheet for the...
I was just asking they were both negative, but it makes sense since the
Yep.
inflow has...
So what do we find? If we just balance the I or the X direction, we find that the P1A1 is equal to... Oops, I forgot one silly thing. What did I forget? What is the force? I need to put more room here. Sorry about that. What is the force that the elbow exerts onto the water. I left that out, what I'm trying to solve for.
Some component in the iron bit direction. Those two components.
Pardon?
It's all of that.
The force that the elbow exerts on the water. First of all, these two pressures are the same and their gauge pressure is 0, and so they go away. It's atmospheric pressure everywhere. On the walls of the pipe, there's atmospheric pressure. Okay, so the force of the elbow is just equal to minus m dot v 1I plus 1j. So we can say, what is the mass flow rate, m dot? That's going to be the density times the volumetric flow rate. And so it's going to be 1,000 times 0.02. It'll be 20 kilograms per second. And then what's the mass flow rate times the speed? Well, I have to calculate the speed. Get up here. Maybe I'll doodle up here. So V is equal to the volumetric flow rate divided by A, 0.02 meters cubed per second divided by pi. The diameter, 0.040 squared times 4. And so what is the speed for this problem? Uh, 15.916 meters per second. And so we're going to have 15.9 meters per second times the mass flow rate, 20 kilograms per second. What's a kilogram meter per second squared? A Newton. And so you calculate that it's 318 newtons. So the force that the elbow exerts onto the water is equal to negative 318 newtons in the I and 318 newtons in the J. That's the answer for part B. But once we know that, what's the answer to part A? Negative of that answer. And then answer to part C. What's the pipe on the elbow? Is this same answer. This is the same answer for A and C. True. Spent a lot of time on that, did I not? Hopefully you can, that makes sense to you. This problem, I collected it last time, but it was just garbage. There's no sense grading them. So, trashed. Okay? But let's solve this problem. Do you remember this problem? Yes. So we have a sluice gate. It's used to control water flow in a 5-meter wide channel. So the depth that you don't see is 5 meters running into the page, the third dimension. The upstream height is 6 meters. The downstream is 1 meter. And the upstream speed is 1.5 meters per second. And a horizontal force is required to hold the sluice gate in position. This is the horizontal force. Neglecting friction and the bottom of the channel, determine what is V2 and what is F. And how are we going to solve this problem? Okay. There's a couple variations of this problem where you would have to use Bernoulli's equation. But because they gave you V2 coming across this whole face right in here, V1, you don't really need to use Bernoulli. I can repeat this problem where you would use Bernoulli, or need to use it, but you really don't need to use it here. Okay. how do I determine V2? Not Bernoulli, but
Conservation.
continuity, conservation of mass. Applied to what? What am I going? I have this principle, the conservation of mass. How do I employ it? What do I apply that statement to? I apply it to a control volume. I have to very judiciously select a control volume. I can select the same control volume that I'm going to do continuity for to get V2, as well as the second part to get F, the force. So let's spend time to get the right control volume. If I'm interested in getting V2, should I cut the control volume over here? No, I need to cut the control volume where I'm interested in the velocity. I need to put the edge of the control volume way over here. Now, just like everything else, do I cut it into the air? And then do I include the force, or what do I do around here? Do I cut it in between the force and the sluice gate? Do I come inside and cut it where in here? Where do I cut that control? I'm trying to make a loop and I have to make some decisions. And then when I come around, do I try to cut through the air, or do I try to cut through the water at some level? And then what do I do over here? I got to come down. Do I go deep into the ground to come across? Or do I try to go right in the water, right at the edge and come across? What I'd like you to do is I'd like you to spend some time, reproduce this illustration, and give me a control volume which will work to both calculate V2 from continuity and F using linear momentum concepts. It's really important here. A lot of people want to come and they want to cut this control volume right in here, and then they come up into the air and they cut across the air and they come down. Or actually a lot of people want to cut this control volume real close. It's like, look at, if you're interested in solving for V2, cut the control volume where V2 is. If you're given some information about V1, cut the control volume where V1 is given. Don't cut it over here and then assume, okay, I'm just going to keep on moving. There you go. I now know the velocity cutting over here. Well, don't do that. Why not just take the control volume to where you know information? So why is coming in here and cutting not so good? And I see a lot of people put this, very, very common. There's the pressure distribution on that boundary of the control volume. Well, it's the pressure distribution on that part of the wall, they're thinking. But take a look very closely. What is the pressure right here in the water? Atmospheric. What's the pressure up here? Atmospheric. What's the pressure here? Atmospheric, 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 atmospheric. What? What is the pressure right there? If it's where some air is, atmospheric. How does it increase, but then do something like this to get back to, I don't know. It's too complicated. Let's leave it alone. It's because the fluid is accelerating in that vicinity. It's accelerating to scoot underneath the sluice gate. Let's leave that part of the problem alone by getting a larger control volume. And the other thing is, if you do cut the control volume up this way, it would need to be a force distribution that's acting on the water, pushing it that way. Right? A lot of people show me the distribution, hypothesized distribution of the force distribution on the gate. But we're interested in things that are acting on our control volume, which would be the water. Okay, so let's not cut there. Some other people say, great, I'll do this. Well, is F inside? I mean, it's an internal force then inside our system. That doesn't make sense. Well, how about this? I'll cut it in half. You know, I'm a compromiser. I'm a budding politician. I'm going to make half happy, half mad, and just compromise. The best choice is right here. So when I come along this side of the outside of the sluice gate, it's all just atmospheric pressure. Oh, but I have 1 point load applied to it. And that's part of my control volume. Then I come up and I go around. I know that there's probably a hinge up here and a pivot, but you know what? Then you would have to worry about that. You can't just come up and then cut through the middle of the gate right here, because there could be some forces through there. You need to cut through the air. Got it? Okay, now once we cut through the air, then we cut through the air. I've got to go through the water. Then I cut, most people did this fine. They don't want to go into the concrete or the soil or anything. They just cut along the edge. Now, you say to yourself, I do have a hydrostatic, because it's far away from the sluice gate, of the water outside the cut, outside the control volume, acting, and it's primarily hydrostatic. Hence, it looks like that. If I start drawing my control volume close in right here, what do you think about the pressure distribution? Do you really think it's going to look like that, acting on that edge? No. No, it's not. So that's why you move far away, and there you go. I have more confidence that it's essentially moving, but it's not, doesn't have a bunch of complicated acceleration field to give me a change in my pressure field. All right. So this is my control volume. I can use it for the conservation of mass, continuity, to calculate V2, as well as the linear momentum to calculate F. That's the hard part, isn't it? So what is my continuity? It'll be the area 1 V1 times rho equal to rho times area 2 V2. The rho's canceled. It's incompressible water. Area 1, isn't that H1 times the width? And then what's my velocity 1? That's given. What's area 2? H2, same width. V2, the widths cancel. And we find that the velocity exit is equal to the velocity inlet times the height difference. And so the height inlet is 6. Height out is 1. It's just V1 times 6. It's so V1 is 1.5, so V2 is equal to 9.0 meters per second. Good? Great. Now the next part, how to calculate that F with that same control volume. So we'll do linear momentum for the control volume. Let's do this. We have some of the forces. What are the forces acting at? Oh, I'm going to have a pressure here. I'm going to do this. I'm going to say this is P1 average pressure, because I know it's a distributed load, but I'm going to, replace it and get the average pressure there, times the area. What is the area? Is that the same area that I had over here? Sure, it's the same area, isn't it? That will push it to the right, so we're going to do linear momentum in the x direction. That's in the positive x direction. How about over here? Do I have any pressure distribution at that cut edge in the x? I want you to represent that one. Is it in the x direction, y direction? And what's it equal to? Not y direction. All right, so what we have is we're going to have P2 average times A2. P2 average would be like this. And which direction is it pushing? It's in the negative, it's to the left. So that negative sign is important, isn't it? Now, any other forces acting on this control volume? Yeah, the force that we have. Now, is it in the positive x or negative x? Negative F. Now we're going to calculate for the magnitude of that force, knowing its direction is in the negative x direction. Now we come over to our linear momentum equation. We had nothing for the transient part, but we did have the outflow. Let's put the outflow first. So we're going to have, forget the beta, the mass flow rate times the velocity in the x out. Okay? What is at the outlet flow? Isn't this over here the outflow? What is that velocity in the x out? Is it V2, positive V2? Now let's finish the equation. We're going to have a minus on the inflows, and the inflow has a mass flow rate, and then we have the velocity on the inflow, and I just want the x component of it. Is it positive V1? Yeah. So let's rearrange this equation. We're going to have F is equal to, I'm going to pause. Are the signs correct?
Yeah.
All right. I like to try to get the equation so you can somewhat read it. Somewhat read it. So the force here to push back, why is it having to push back? Well, pardon? I have a sign error. This is supposed to be a plus right here. That's supposed to be a minus right there. Now let's take a look at it. What do you think? That looks better. Okay. Maybe this one. F, if I have this linear momentum flow rate coming in at 1, I have to stop it. If I could just brought it to rest completely, nothing else happened, it would be F would be equal to m dot V1. True? But then I have to push out m dot V2, which is meaning that F is not in the positive. It's going to be in that direction to push it out with a positive V2. So the sign makes sense, and that term makes sense. And then right here, I have that F is equal to P1 average A1. I have to counteract the hydrostatic on the inlet. But I don't need as much because I have a little hydrostatic on the outlet to help me. Okay, you could try to make interpretation of your equations. I would encourage it, but it's not necessarily. All you have to do now is substitute numbers and compute. So what do we have? We have minus the mass flow rate. Did we ever calculate the mass flow rate? It's the rho, it's 1,000 kilograms per cubic meter times A1 V1. A1 is H1, 6 meters, times the width, 5 meters, times the V1, 1.5 meters per second. So we calculate the mass flow rate, 45,000 kilograms per second. It's a lot. Okay, so we're going to have minus 45,000 kilograms per second times V2. V2 is our 9 meters per second. Then we're going to have the 45,000 times 1.5. Then we'll have minus, what's the average pressure at 2? P average at 2. P average at 2, or 2 average. It's going to be 1/2 rho G H2, isn't it? And so you calculate the P average at 2, it's like 4.905 kilonewton, and then you multiply by the area at 2, which is height 1 meter times the width of 5, you get 5 meters squared. And then over here we're going to have the P average at 1. That P average at 1 is going to be 29.43 kilopascal times the area at 1, which is 30 meters squared. So the force is going to be from this large term right here, 882.9 kilonewtons. The second term, so that's this term, the first term. The second term is at negative 24.5 kilonewtons. And then this term is a 67.5 kilonewton. And this term is a negative 405 kilonewton. So you can see the relative magnitudes of the terms. When you sum them up, the force is 521 kilonewton. And it's applied in the direction that's shown on the sketch. What would happen if you put a hinge up here? Well, then you've got to do the moments around the gate, and it's back to statics. It's a little more work, but the net force in that on the gate in the x direction is that many newtons. I didn't say where it needs to be placed, or if the hinge can contribute something at the top, or something like that. We didn't do that. Okay? What did this emphasize? Spend some time getting the right control volume. If you get the right control volume, a lot of things fall into place easier, okay? I don't think I have time for this one. Or, well, this one. Well, sometimes you have a rocket. A rocket burns fuel. So here's my rendition of a rocket, and it'll have this as a nozzle. That's a bad-looking rocket, isn't it? And what happens is you just have some fuel stored in the rocket, usually some fuel here, mixture there, and then they're combined, and there's combustion, and what comes out of the end of the rocket is some combustion products due to the fuel. But you're not getting air from the ambient. You really have maybe liquid oxygen inside the rocket. Okay? So everything that comes out of the rocket is what was inside the rocket. Okay. So when you have a fuel burning rate of 2 kilograms per second, that's what's coming out of the rocket. Okay, there's nothing coming into the rocket. So if you do a control volume around the rocket, you're just going to cut a bunch of air, and then finally you have only one flow rate out. Only one zone where the fluid is flowing out of the rocket. That makes sense? All right. All right. And it comes out with a high speed V of 1,300 meters per second. Now, if you don't want that rocket to move while it's throwing out the products of combustion, you're going to have to apply a force to hold it stationary. True? Maybe I should cut the control volume right at the tip of the rocket. And that force that you're going to have to apply when the rocket's throwing out the fuel, combustion products that direction, downward, are you going to have to apply a force F to the rocket to hold it down? Yeah. This is just like our force that the pipe exerts on the nozzle, then the force that the nozzle exerts on the water, and the force that the water exerts on the elbow or whatever. So what you have is if you could do one control volume, it's only the fluid, only the fuel. And then another would just be the shell. Or as I've shown, one is the fuel, the shell, and then we have an external force. But on the shell, the fuel will exert an upward force on the shell of the rocket, and the shell will exert a downward force on just the fuel. And so this would be the shell of the rocket on the fuel. This would be the force of the fuel on the shell. And this is the force, what do you want to call this one? Some external force on the shell. True? Okay. Well, normally we don't build rockets so that we can light them off and then hold them down on the pad and let them sit there. Right? Normally this is equal to 0, but that would be the necessary force to hold it stationary. But because you're not holding it stationary, A is now not 0. It's accelerating. It's going to accelerate. True? So what do we call this force that would be necessary to hold it down? Our thrust force. It's as if this force, this rocket feels an upward force called thrust. And that upward force called thrust is the product of the mass flow rate of the fuel going out and the velocity going out the opposite direction. How many people thought about thrust before, dealt with thrust, worked with thrust, right? So that's what it is. It's that product. So if you multiply 2 kilograms per second times the 1,300 meters per second that it's being exhausted at, you will get that so many newtons of thrust, which would be 2,600 newtons or 2.6 kilonewtons. That's the thrust force. That would make that rocket want to lift. What's it come from? Expelling the products of the combustion out the bottom. All right. So we have a number of problems dealing with carts and turning vanes on carts. I think we've solved these before. If the cart's stationary, then you have to hold it with a particular force. Let's say the cart has a state of motion which is 2 meters per second toward the vane. What do you think about F of H? Will it be higher than it was before? The same or lower? It'll be higher to push it at a constant speed in. True? All right. I encourage you to take a look at some of these problems. I think I spent too much time on the other one. The linear momentum correction factor, beta. Well, if I have a pipe flow and I have velocity distribution in that pipe, and so it's going fast in some locations and slower in some locations, but I want to use a simple equation that the mass flow rate times the average velocity in the pipe times a correction factor is equal to the linear momentum flow rate if I did a detailed integration over all of the area over which it outflows across that pipe. Okay, well, what would be the linear momentum flow rate? Well, we'd have the velocity at that location times the normal vector. Well, the normal vector, so it's just one directional. Just the velocity at that location, a function of r. You could think of that as function of r. Radius, here's radius going out. Things are symmetric in a round pipe. And then you have the mass flow rate, and then you have the velocity as a function of r. Is that our linear momentum flow rate? So if I could do this integral, it'd be perfect. I'd be able to calculate it. Okay. Here's beta. What is m dot? Rho area, V average. Then you multiply by V average. So what we have is we have rho, V is a function of r squared, dA. Can we cancel the rho's? Sure, it's incompressible. And we get the equation for beta. Beta is equal to 1 over the area, the integral of the velocity as a function of location divided by the average velocity, quantity squared, dA. And there's our equation to get the linear momentum correction factor beta. So what you can do with this is you can assume a particular profile. Here is u as a function of r is equal to u max, 1 minus r over cap r, all of that to the 1/7 power. And you could say, okay, give me the average velocity, give me the linear momentum correction factor, and then you can go back and also calculate the kinetic energy correction factor. I don't like to integrate by hand. And you set up those integrals, you can use Wolfram alpha, and what you can find was that the average velocity is 49/60ths of the maximum for this velocity profile. And you can also calculate both the alpha and the beta, and they're pretty close to 1. So the kinetic energy correction factor and the linear momentum correction factor. What we need to move into in the next 50 minutes, 55 minutes, is angular momentum. So let's do that. So here are the equations that we've been using for the linear momentum, both as a surface integral as well as over the average over some inlets and outlet ports. Here is the angular momentum equation. It stems from the same basic equation. What is the starting equation? From the Reynolds transport theorem. What is being transported through the system, through that control volume? And so we have not just linear momentum, we have angular momentum. That's why a good background in dynamics is important for this class. What is the linear momentum of a mass particle, mass m, traveling with the vector velocity v? Isn't it just m times v? But what's the angular momentum of that particle? You have to have some sort of coordinate system, and you have to have some sort of description of r. True? And now we could talk about the angular momentum of that particle about the point from which r is measured. Maybe you call that the origin. True? And so what would be the angular momentum? Is it r cross mv? Is that from dynamics? Do you remember something like that? Is it r cross mv? Yeah, it's like a moment. Okay. So here is the r cross mv flowing out, and here's the r cross mv's flowing in. And this is if you have some accumulation or depletion of angular momentum in the system. And then what is this over here? Well, it's analogous to what was over here. What is this sum of what? The m's, big M's, sum of molar masses? No, sum of moments. Moments acting on the system. So what can increase or decrease the angular momentum flow rates are moments, just like forces and could do the same for linear momentum. Often it boils down to something very, very simple for some problems, but you don't want to just boil it down too quick. But often we have a rotational system and we just apply a torque to a rotating shaft, and there you go. And it's changing the flow, the fluid flow's angular momentum as it goes through a control volume.
Those are flows only in the plane of...
Well, this is all vector entities, and then what we do is we apply it typically to a system where it's rotating in a plane, and I'm having to apply a torque to a shaft that's perpendicular to that plane. Yeah, that's I think what you just said.
Right, so if there's any flow up.
Yeah. Let's solve this problem. So we have water sprinkler. It has two sprayers at the ends, and they're both 120 millimeter long shafts. So from this point to that point, it's 120 millimeters. It's in the middle, sorry. From this point to that point is 120 millimeters. Okay. Then the water then is turned 90 degrees, so it's turned 90 degrees, and then it shoots it up 30 degrees. So you see what's happening? It comes out, there's a kink turning at 90, but also a bend to kink it up 30. And there it then shoots the water upward into the air through a nozzle end that has a diameter of 4 millimeter. It's rotating with a rotational rate of 35 RPM. And there's a total flow rate of 0.125 liters into the sprinkler. So Q into the sprinkler is 0.125 liters per second. How many kilograms per second is that mass flow rate for water? Kilograms per second, isn't it? And then what is the flow rate in each of the two? There's two legs or shafts or two sprayers for this. Wouldn't it be half? So this is m dot divided by 2 going out to that side, m dot divided by 2, and you can do the math. What is it? 0.0625. Okay. Calculate the friction torque at the sprinkler pivot. Well, if it's rotating this way and it's ejecting water here and here, let me first ask this. Can you visualize the way it's rotating? And is the water helping it rotate in that direction by the way it's being thrown out at the ends? Yeah, it's causing it to rotate. There's no external applied torque to make it rotate in the direction that it's rotating. It's basically rotating in that direction because it's throwing water out the ends. Okay, but there's a friction torque at the sprinkler pivot. If this is a real problem, which way would the torque be applied to this the sprinkler pivot? Against the direction, wouldn't it? So the torque would be in this direction, and we can use T for torque. Some symbol for torque, okay? Or you could use moment of the force, and you know that that's torque. Well, how in the world are we going to solve for the torque? You have to do angular momentum, that's right. So I know that I emphasize a lot about the control volume. Because this is a three-dimensional problem, it's hard to draw the surface that encloses it. If it's 2D, it's a line. But I'll still draw it as a line. It's got a cut right there. It's got a cut right there. And then it's going to come down, and it's going to cut where the torque is applied to the shaft, and then it's going to cut where the inflow is and come up and then come out and like this. Does that make sense? So there's only going to be one torque applied to that control volume, and that's T. And you have one inlet mass flow rate down here coming in, and two exit mass flow rates at the tips out of that control volume. All right. So what was our general equation? We said, well, any sum of the moments that are externally applied to our control volume, and I'm going to dispense with the accumulation or change of angular momentum. And then we have for the outflow, you're going to have the plus R cross M dot V on the outflow minus R cross M dot V for the inflows. Okay, because we don't have any transient, let's say that there's two outflows. We're going to do R cross M dot V. Let's call this one 1, and call this 2, and call this 3. And so this is the inflow at 1. We have out at 2 and out at 3. What do you think about the magnitude of these two? They're going to be the same. They have the same length of the arm, the same tilt up. Right? They turn 90 and then tilt up 30 degrees. So let's do this. let's work on this term right here. That's our inflow at 1. Okay. What is the direction of our flow coming in? It's just completely in the K, if you want to think about it in 3 dimensions. But where are we rotating about? What axis are we rotating about? The K. So does it have any angular momentum coming in? None. So this term is 0. Okay. Now the hard part. We have fluid flow over here flowing out. So that m dot, let's just deal with one of them. So this is going to be 2 times r cross m dot v, okay, on the exit. Okay, first of all, can I pull out this mass flow rate? Sure, it's constant. And guess what? 2 times that mass flow rate in one arm, 1A, and the mass flow rate in 1A is equal to half of the total inflow mass flow rate. So that's equal to the total mass inflow flow rate divided by 2. And guess what happens to the because both of the arms are symmetric. Okay. But this mass flow rate is now the total inlet flow rate. Now what do we have? We have R cross V. R cross V. Well, we're going to come out from this axis, true? And we want it to be spinning around this axis as shown. If it comes out the end at velocity v, it'll have an upward component and a sideways component related to that angle of 30 degrees. The upward component will be v out times sine of 30. The other one will be v times the cosine of 30 degrees. Which of the two? The upward makes it want to spin around the axis, or the sideways make it spin around the axis? The sideways. It's the v2 cosine of 30. So when we do that r cross v, isn't that simply the perpendicular distance? Let me put it as just r. R equal to 120 millimeters times v, which is going to be the external exit velocity off of each tip, times the cosine of 30 degrees. This is the torque. I'm sorry?
That's state 1.
Let's take a look looking down at that term. It's going like this, right? So we got that component, but it's rotating, isn't it? And because it's rotating, I want to capture the relative speed that it's exiting this control volume here. So the tip is moving at a rate of omega times r, or lowercase r I think I used. Is that lowercase r? Yeah. Omega times r. But it's being issued out of v times the cosine of 30 degrees. So what's the relative speed that it's actually leaving the red control volume? It'll be v relative will be v cosine 30 if it wasn't moving, minus omega r because it is moving.
That's what I mean. Like
so I need to put
omega, right?
Omega r right there.
Close it down from the first time to the
So the 35 revolutions per minute convert to 3.665 radians per second. And we know the moment arm distance, and so the velocity turns out to be this relative velocity right here is 3.867 meters per second. A little bit of work to get the V here because of the nozzle and the linear the volumetric flow rate out each side, but it's doable. And then we multiply by our distance and our mass flow rate, and we get that the torque applied is equal to 0.058 Newton meter. And so it's applied in the opposite direction. How it's currently rotating at 35 RPM. Let's say this T goes to 0, it'll actually go faster than 35 RPM. I don't think I calculated the steady state speed, but what it would be was this term would have to be equal to 0. So omega with no torque, that would be the maximum omega, would be this V cosine 30 degrees divided by R, whatever that gives you. Well, the consideration of angular momentum flow through a system is very important to analysis of water pumps. What's a water pump? You have some inflow, often it's coming in radial. It hits a set of impeller blades, and this is a cross-sectional look. This is a top-down look. The impeller blades can have quite complicated shapes, or some can be very simple. But here it's complicated in the sense that you have it changing as you're going out radius. It's like cutting it and turning it. I'm trying to use my hands to show you, but it's cutting it and turning it as it flows from the inlet radius to the outlet radius. And it's turning it so it's flowing. Here it was flowing axial. Here it's flowing radially out. And so that's the transition that happens to the water in the impeller. And then when it comes off the tip out here off the edge of the impeller, they're showing by the dashed line sequence of positions of the tips of the impeller. The water is sort of slapped out, thrown out. You can see the velocity vector of the water they're trying to illustrate. It's then caught in a increasingly large region, a volute region, and then there's a cut right here, and it's thrown out, and that's a water pump. There's lots of water pumps. And so what happens is you have a shaft that is making the impeller system rotate, and it's ingesting. You can think about it from an angular momentum flow rate of the water. Very little angular momentum flow rate coming in to the impeller region. A lot of angular flow rate going out from the impeller region. So in the I region, the inflow has almost nothing, or essentially nothing for the angular. But on the outlet, it has a lot of this. So the control volume is shown right here with the red dashed line, the outer boundary of the impeller region. And you have some inlet right here, region to the I region. Okay. There's some dimensions that are important. What is R1?
The radius of the inlet.
Yes, the I region, and the R2, the radius of the outer impeller. What is this B1? That's complicated. What is B1? It's the height of the water passage in the I region. Does that make sense? And then what is the B2? Do they show you the B2? Here's the B2. It's kind of out here, right there. It's the height of the water passage on the discharge from the impellers. Maybe we should show it right here. That's B2. And this distance right here to right there is B1.
The gap that it flows through.
Right. So you can have typically B1's larger and then B2 is smaller. Because the water is going a lot faster. You don't need a large area. The water is going a lot faster as it comes off the tips than in the I region coming in.
From like centrifugal acceleration.
You bet. It's being thrown out.
So they don't decrease the size to...
I'm going to go. All right. So we do have this shaft. What is the shaft doing? It has some rotational speed and some torque in the shaft that continuously is changing the angular momentum flow rate of the water through the system. So this is the control volume. This is the rotational speed, the torque in the shaft, the inlet radius, the outlet radius. They'll have a B1 for the height and a B2 for the height of the passage coming in and out. And then on the inlet, they're showing you that they have, what is V1? That's the velocity vector coming in, and they're very much interested in decomposing that into two directions, V1N and V1T. What does the subscript 1 mean, inlet? What's the subscript N and T mean? Normal and tangential, right? So if you're changing the angular momentum flow rate around point O, the inlet flow, what gives it the inlet angular flow rate, angular momentum flow rate? Is it a large V1N or V1T? V1T is what makes a non-zero angular momentum flow rate about zero. The V1N makes nothing in the contribution of the angular momentum flow rate. That's right. The velocity vector, the R cross that V1N is zero. The R cross V1T is simply the R1 times the magnitude of the V1T. So, how about on the outlet? Same thing. They could have shown it out here, but things get cluttered, so they just moved it, back a little bit so you could see. That's the radius. It'll have a height B2. Then it'll also have the decomposition of that vector V2 into two components, the tangential and the normal component. The normal component really is not contributing to the angular momentum flow rate of the outflow. This one does a lot. That's the angular momentum outflow, V2. And so if we could, let's just write down our equation and say we have some sum of the moments acting on this control volume. And we're going to have the unsteady term, but that's zero. And we're going to have the outflow terms, only one outflow term, R cross M dot V2. That's the outflow. And then we're going to have minus the R cross M dot V on the inflow. Okay? Let's do this. So, I shouldn't have put a 2 there. I should just say this is out and this is in. Okay, for this problem, the only thing that is externally applying a moment to this control volume is the torque supplied by the shaft. And we're doing it now, this is 3D, but we're going to do it for the axis running perpendicular to the sheet of paper into the third dimension. So when we do the outflow, it's going to be the R2 cross mass flow rate V2. And we can now do that cross product, and we see that it's just going to be R2, that length, perpendicular distance, and M dot, and V2T, that scalar component, the tangential component. That makes sense? Similarly over here we have the R1 cross M dot V1, and that just boils down to R1 M dot V1 tangent. So the torque that the shaft has to supply is equal to this minus that. Or you can pull out the mass flow rates, and it's just R2 V2 tangential minus R1 V1 tangential. Let's go back and look at that equation that was written right here. Not that one. Where did I just see it? Oh, right here. Isn't that the equation for the motor? For the water pump, I mean? So we understand now this simplified application of the angular momentum flow rate. Ready to solve a problem? A centrifugal water pump with impeller diameters of 14 on the inlet. So R1 is 7 centimeters. If the diameter is 14, the inlet radius is 7. And then the R2, if 32, that's 17 centimeters, right? No, 32, 16 centimeters for R2. And it rotates at omega equal to 900 revolution, 2 pi revs per minute, 60 seconds, and you can get this now in radians per second. Has a mass flow rate, m dot, of 95 kilograms per 60 seconds per minute. Assume the tangential fluid velocity is equal to the blade angular velocity both at the inlet and at the exit. So what are they saying, that last sentence? The tangential fluid velocity is equal to the blade angular velocity. So it's as if let me draw it like here's the point. You come out, there's R1, and so V1 tangential is equal to the rotational speed R1. And we come out, there's R2. V2 tangential is omega R2. Same omega, just different R's. Calculate the power required to run the pump. Well, what's the W dot for the pump? It's equal to the torque shaft times the rotational speed of the shaft. Is that good? Or not good? Do you agree? Yeah. And how do I calculate the torque in the shaft? Isn't it the mass flow rate of the water from angular momentum consideration times R2 times V2 tangential, which we just worked out to be omega R2, minus R1 times V1 tangential, which is omega R1. And omega is right up here.
Don't you have to multiply that whole thing times omega?
Well, this is what is the shaft. And then I multiply by the shaft to get the power. When I solve this problem, I get that the rotational speed is 94.25 radians per second. And the mass flow rate's given. And the shaft torque in the shaft comes in to be 3.09 Newton meter, and the W dot to run the pump is then 291 watts. Well, any comments or questions on that?